Okay, so earlier we learned how to deal with circuits that have multiple voltage or current sources. And this becomes particularly sometimes tricky in AC form. So now that we're in AC, we have to be careful with the frequency. If we have more than one source in a circuit, like I have V1 and V2 here in this circuit, then I have to check what their frequencies are. So in my case, V1 is given by this equation, 10 cosine of 2t, means its frequency is 2 radians per second. And this is supposed to be V2, it's given by just 5. There's no time or anything from that. It's not as a function of time, so it means it's a constant 5, or it is DC. That means its frequency is really 0, whereas V1 had a frequency of 2 radians per second. Since these are different frequencies, I have to solve them with a technique called superposition. Basically, what this means is I solve with my first source on and turn all other sources off and find whatever you're looking for just with that first source. So in my case, what I'm looking for in this circuit is the voltage across capacitor 2. So voltage from here to here from it. I find this with just V1 on first, turning V2 off, and then I go and solve for it with the second source on. So then I have V2 on and I turn V1 off. I repeat for this as many different sources that I have that have different frequencies as possible. You could have 10 different sources with all different frequencies. At the end, I add the contributions from each source as a function of time. So it's important that I can only do this in time domain when it looks like things like cosine 2t stuff. I can't add in phasor or rectangular form since they have different frequencies. So we're going to do this here. And I have two sources, different frequencies. So I'm going to look at one at a time and then add their contributions at the end. Okay, so I'm going to look at this first with just voltage source 1 on. So V1 as a phasor was 10 phase angle of 0. Remember, it also had a frequency of 2 radians per second. That means I get to turn every other voltage or current source in this circuit off. I have another voltage source here, V2. To turn a voltage off, that becomes a short circuit, so make it just a wire. That means that C1 and R3 are also short circuited. They now can have no voltage drop across them since there's a wire going where they go, which means they have no current through them. So they don't really play a role in my circuit at all. So my circuit can be simplified by just V1, R1, R2, C2, and R4. So I have that wire going in between it there. C1 and R3 are no longer playing a role. I now notice that R2 and R4 are in parallel here. So in parallel, they combine to get me an equivalent resistance of 26.667. I also have C2, and there it's in parallel with R2 and R4 as well. To combine it in parallel, I need to do that as impedance. Remember, the impedance of a capacitor is 1 over Cj omega. So its C is 0.02 since it's 20 millifarads. Frequency, remember, was 2. J, that becomes 1 over J is negative J, so negative 25J for that impedance. Now I can combine it in parallel with my resistance parallel, and I get, this is my resistance times my impedance. Again, if I'm in impedance form, I get to act just like it's a resistor. So to combine in parallel, I multiply on top, and I add on bottom. Add this plus this. This is impedance of my resistor plus impedance of my capacitor. Okay. That gets me. I need to put these in phasor form to actually multiply and divide. So negative 25J becomes 25 phase angle negative 90. Now my denominator, I now have a complex term that I calculate the magnitude for by taking the square root of 26.667 squared and negative 25 plus negative 25 squared. That gets me 36.5531, and I found a phase angle by doing the inverse tangent, remember, of negative 25, since that was my imaginary, over 26.66. That gets me negative 43.152 degrees. I can now combine by multiplying and dividing. So I multiply 26.667 times 25 divided by 36.5531, and I get 18.2385. And for my phase angle, I have 0 plus negative 90 minus negative 43.152, and that gets me negative 46.85. That's my equivalent impedance of all three of these guys, R2, R4, and C2 in parallel. I can now find the voltage across them, which would be the same since they're in parallel, by saying my circuit has now combined to this, a single Z equivalent place those, still R1. So the voltage across that Z equivalent I can find by doing the voltage divider. Just like, again, if it were two resistors, as if I'd had R1 and R2. They're now in series. That Z equivalent is now in series with R1. So I take my total voltage, multiply it by what I'm trying to find the voltage drop across, that's the equivalent in my case, over my total impedance, the equivalent plus 20. So that was the 20 ohm resistor for R1. Plug those numbers in. V1 was 10 phase angle 0. Plug in Z equivalent, and I get this. I notice on my denominator I have 20 plus some ugly phasor. Can't add in phasor form, so I need to convert that to rectangular. So in rectangular form, I take 18.2385 cosine negative 46.85, and I get 12.474. I take 18.2385 sine of negative 46.85, and I get negative 13.305J. Okay, I then can now combine terms. I have two real terms in my denominator, 20 plus 12.474, and only one imaginary term, only one J number. The 20 plus 12.474 gets me this. Everything else stayed the same. And now that I have a single real number and a single imaginary number, I can make that into phasors, so I can divide. Again, calculate the magnitude, square root of 32.474 squared, plus negative 13.3057 squared will get me 13.059 as a magnitude. Phase angle from doing the inverse tangent of negative 13.3057 over, or divided by 32.474, gets me negative 22.28 degrees. And I can now multiply and divide my whole equation. I now have 10 times 18.2385 divided by 35.09, that's me 5.198 for my magnitude. Phase angles. Multiplying, I add phase angles, so 0 plus negative 46.85. Dividing, I subtract, so minus negative 22.28, and I get negative 24.57 degrees. That is the voltage across the equivalent, which is the same as the voltage across that capacitor. And I'm writing it as a voltage CS1. That S1 stands for it's the voltage across the capacitor from source 1. That was all I was looking for. Remember, I only had V1 on here. I'm now going to have to do the same thing with just V2 on, and then I can combine those together. So, but first of all, let's put it as a function of time. So my voltage across that capacitor, C2, just from source 1, so VCS1, I take my magnitude, 5.198, write as a function of time, I write that magnitude, cosine, pull back out my frequency, 2t, minus 24.57. Now I get to do this with the second source on, so now with V2 on. I turned V1 off, it became a short circuit. What I notice is that V2 here, remember, was just 5, plain old 5. This is DC. This means our frequency is 0 because I don't see anything as a function of time. Under DC, remember capacitors are open circuits. So I had a capacitor here and I had a capacitor here, but I've replaced them with just open circuits. Since this is now a DC circuit with only V2 on. In this case, I now notice that my circuit looks a lot more simple. I can draw it as, here's R1, here's R2, here's my voltage source, here's R4, and that's it. R3 is going to nowhere, so it doesn't really do anything. This is my whole circuit. R1 and R2 are now in parallel with each other. Combine them and get a resistance of 13.33. R3 is going to nowhere, it's going to an open circuit, so it doesn't count anywhere in it. It won't have any voltage drop, won't contribute to my circuit. since it was in series with that capacitor. So this means that the voltage drop, which I was looking for across C2, is the same as the voltage drop across R4 here, or my 80 ohm resistor. So the voltage across my 80 equals the voltage drop across capacitor 2 from source 2 effect. So I can do that now by voltage divider. Once I've combined R1 and R2 together, I basically have a circuit that looks like this. It goes from the positive end of my voltage source to that R equivalent, then to my 80 ohms, and back to my voltage source. So how do I find the voltage drop across just that 80 ohm resistor? Well, that's my total voltage drop, V2, times that 80 ohm over the total resistance, 80 plus 13.33. We calculate that, and I get 4.28 volts. And now I get to add the voltage contribution from source 1 plus the voltage contribution from source 2 for what I was trying to find, which was my total voltage drop across capacitor 2. From source 1, remember I had this equation as a function of time. That source 1 had a frequency of 2. This is my voltage drop from source 2. It has an implied times cosine of 0t, but since cosine of 0 is 1, it's really the same thing as not writing time there. It's just 1 times 4.28. That is my whole voltage as a function of time from this, to look at that a little more clearly. So this is my answer using superposition to solve for the voltage across that capacitor due to both sources in my circuit that had different frequencies. I really have no choice but to use this technique of superposition to do this, because otherwise I don't know what frequency to use when calculating things like the impedances of my capacitors. Okay, let's also look at what other circuit techniques we can do in AC form. Basically, all of our rules still apply. Our math just gets a little more complicated now that we're in phasor form. So we can do mesh or nodal analysis in phasor form, so with AC circuits. So for example, if I have this circuit here and I want to solve it with mesh analysis to find my mesh currents, I would have a current I1 for this mesh and a current I2 from this mesh. I calculate the impedance of my capacitors. In this case, I've been told a frequency that is assumed to be the same for both sources. Both this voltage source over here and this current source over here should have a frequency of 0.2 radians per second. So I don't have to do superposition. I can just do normal mesh, leaving both sources on at the same time. When I do that, I can calculate impedances since I only have one frequency. Impedance of capacitor 1 comes out to negative 2.5J. Impedance of capacitor 2 comes out to negative 1.25J. I then can write my mesh equations. So for mesh I1, going around clockwise, I hit the negative sign of this voltage source, so negative 5 phase angle of 10. This is a voltage source, note the plus and minus. Plus, I hit all these circuit elements, R1, C1, R3, and capacitor 2. So R1 plus, this is Z of C1, this is R3, this is Z of C2, times I1. All of them will be positive for I1. The only thing I have overlapping with I2 is ZC2, and so I'll have minus ZC2. I do recommend writing this out carefully like this because the signs can get confusing. Notice here I have a minus negative 1.25J. That's because the impedance itself was negative. So I have to be really careful with those signs. It's going to end up as a plus, but for right now I'm writing that as minus. From mesh I2, what do I have? Well, I can try going around the impedance of the capacitor, but then, I'm stuck with this. Why? This is a current source, not voltage. What do I have to do with current sources in mesh analysis? Well, a current source should tell me what my mesh currents are. This current source only overlaps with I2, so I can write the equation that I2 is equal to that current source, except for what direction is I2 going. I always define mine clockwise. This current source is going the opposite direction as my clockwise would be through that branch. So it is negative that source. So negative 3 phase angle of 0 is I2. Don't forget that. That's still our normal rules for mesh analysis with those signs. So now I go back in and look at my mesh 1 equation, and I plug stuff in. Instead of writing this phasor, -5 phase angle 10, I'm going to write it out in rectangular form. Be careful when you do that, that negative applies to the whole thing. So I had -4.92 and -0.868J that I got from taking 5 phase angle of 10. So doing 5 cosine of 10 got me 4.92. Stick a negative sign in front of that. And 5 sine of 10 degrees got me 0.868. Stick a negative sign in front of that and a J as well. And I leave the rest of the same. 1 plus -2.5J plus 3 minus 1.25J times I1 times EC2. I2, I now get to write just -3. Or you could write -3 phase angle of 0 if that makes you happy. Same thing. Now what do I get to do? I'm going to try to combine some things. So for I1, I had a whole bunch of things multiplied by I1. Real number wise, I have a 3 and a 1, that gets me 4. Imaginary number wise, I have -2.5J and -1.25J. That gets me -3.75J times I1. And I'm going to move all things not multiplied by I1 to the other side of my equation. So that equals, I have, this is also not multiplied by I1. Move it over to this side of the equation. That was negative times -1.25J times -3. Whole bunch of negative signs there. That really got me -3.75J. Move to the other side gets me positive 3.75J. Be very careful with your signs. That's what I get there for that term. Then when I move this term over, I get positive 0.868J, positive 4.92. Now I get to combine some terms. I have two J terms, this J and this J. So only one real term, 4.92. Combining my J's, I get 4.618J. Putting that in phasor form, taking the magnitude of this, square root of 4.92 squared plus 4.618 squared gets me 6.675, and the phase angle of 43.1865 degrees. Really have that whole thing still times my original one I had over here, I1. Now I'm going to write this out again so we can see that. That whole thing times I1 equals that phasor. Now how do I solve for I1? I just take this number and divide by this number. They are phasors. I know how to divide. So I1 equals that divided by that gets me 1.22 by taking 6.675 divided by 5.48. Phase angles, I get 43.1865 minus -43.15. Gets me around 0.0365 degrees. That's my answer for mesh current I1. I already knew what I2 was, so I've now solved for everything. Remember, if you didn't, if I was looking for the current through R3, that would just be I1, and I've now solved for that. I want the voltage drop across R3. All I would have to do is take I1 and multiply it by R1. If I wanted the voltage drop across C1, I could take I1 and multiply it by ZC1. Once I've solved for those mesh currents, I know everything really that I need to know about my circuit. Let's try another one doing our other technique, which is nodal analysis. So let's pretend I have this circuit now. Now I want to solve for everything I could possibly want to know using nodal analysis. So if I do that, I have certain nodes. I have a node over here. I'm going to call that V1. And I have a big node here. Remember, any node just fires another node. V2. And down here I already had ground, so I don't have to write equations for it. What is my nodal voltage at V1? Well, V1 is just equal to that voltage source since it goes from ground up to that voltage. 10 phase angle 45 degrees. But V2 I don't know. So I'm going to need to solve for that. Okay, before I start solving, I'm going to calculate impedances for my capacitors. And I'm given a frequency, so I can calculate their impedances. Impedance of capacitor 1 comes out to -200J. impedance of capacitor 2 comes out to negative 100J. Again, as a check, impedance of our capacitor should always be a negative J, because I have that 1 over J thing. Always should end up in negative J. So at node V2, how do I write my nodal analysis equation? Well, I'm going to pretend I have a current going in this way. We'll call that I1. I already have a current source going through that branch. That's 2 phase angle of 0. I have a current going down through this capacitor and a current going down through this resistor. Okay, so we'll call those I3 and I4. Into node V2, for writing I1, it goes from what voltage to what voltage? It goes from V1 to V2. So V1 minus V2 over what? If it were just resistors, you'd say over R1, and then if this were a resistor, R2. But it's not resistors, I have R1, then I have a capacitor, so I have to write the impedance of capacitor 1. But they're both in series that I had to go through for I1. So this is my total impedance from them. Anything else going into node V2? Well, I have this current source here. That's just equal to whatever that current source says. In my case, that's 2 phase angle of 0. So all that I have going into node V2. Now what's leaving is my I3 and my I4. This whole term here is my I1. I3 can be written as V2 minus 0, or just V2, over the impedance of capacitor 2. I4 can be written as V2 minus 0 over R2. Let's plug some things in for that now. So in place of V1, I get to write V1 was 10 phase angle 45. V2 I don't know, that's what I'm going to solve for. In place of R1 I get to write 50. And in place of ZC1 I get to write negative 200J. 2 phase angle 0 is really the same thing as 2. In place of ZC2 I get to write negative 100J. And in place of R2, I get to write 100. Just plugging in there. Now, I have really 10 phase angle 45 minus V2 over this whole thing. So I'm going to split those into separate terms. I'm going to say 10 phase angle 45 over this. That's that term. This denominator I've now made into phasor form here. That's all that's happened. And then I have minus V2 over this term. Minus V2. And that denominator put as a phasor is 206.155, phase angle negative 75.96. The rest of this stayed the same, so plus 2 equals V2 over negative 100J plus V2 over 100. Now I get to choose to do something. I'm going to choose to multiply this whole scary equation by negative 100J, which is the same thing as multiplying by 100 phase angle negative 90. Why did I choose that? Because I have that as a denominator right here in this term. So let's see what happens when I do that. I have 100 phase angle negative 90 that I multiply by this first term, just right out here. Then 100 phase angle 90 that I multiply by this whole second term here. That came out there. Plus 100 phase angle 90 times my 2. I wrote 2 now as phase angle 0, so I know how to multiply. Equals 100 phase angle 90 times V2 over that negative 100J is 100 phase angle negative 90. That's what I chose to multiply by. It's finding my like a common denominator, except in this case it won't actually be common. V2 over 100, and I have 100 phase angle negative 90 times that V2 over 100. That 100 written as 100 phase angle 0. That gets me a whole bunch of stuff. This whole first term is just in phasors. I can multiply and divide with that. 100 times 10 divided by 206.155 gets me 4.85. Negative 90 plus 45 minus negative 75.96 gets me 30.96. For my next term, I just left the minus sign out here. So minus 100 divided by 206.155 gets me 0.485. And negative 90 minus negative 75.96 gets me negative 14.04. That whole thing was times V2, so I have my times V2 here. My next term is just 100 phase angle negative 90 times 2 phase angle 0. That gives me 100 phase angle negative 90 equals, luckily this was a term I was trying to cancel out, so 100 phase angle negative 90 divided by 100 phase angle 90 cancels out, just get V2. And then I have 100 phase angle 90 over 100 phase angle 0. That just gets me 1 as magnitude, still phase angle negative 90, like that, times V2. Whew, seems like a lot of work. I'm running out of space here, so I'm going to move to a new page. Copy this line over. So that was the line we just had there. Now what am I going to do? I'm going to combine all terms that are times V2 onto one side and all terms that aren't times V2 on the other. So I had this term and this term. That moves here and that moves here. And this term was times V2. It's going to move over to this side of the equation. That's all that happened. It got moved over here. Now that I have my like V2 terms on one side, I hopefully can combine some of them. So over here on my left side, these are phasors, and I now need to add them. To add them, they need to be in rectangular form. So I take 4.85 cosine of 30.96. I get 4.159. I take 4.85 sine of 30.96. I get 2.5j. And then I have 200 phase angle negative 90. That gets me negative 200j equals V2 onto what? Well, I had a really 1 times V2 here, so 1. Negative 1 phase angle 90 is negative 1j. This was all times V2. The real part of this, 4.85 times cosine of negative 14.04, gets me 0.47. 4.85 times the sine of negative 14.04 gets me negative 0.11766j. That whole thing is times V2. Looks scary, but I've now at least got V2 by itself times something scary equals something scary. Let's see if we can fix our something scary terms. So I get to combine imaginary terms here. I have negative 2.5j minus 200j. Gets me negative 197.5j. And V2, I just copied that whole line over again. V2, my real terms, I have 1 plus 0.47. That gets me 1.47. I have negative 1j and negative 0.11766. That gets me negative 1.11766j. Over on this side, I've now got just a single real and imaginary term. Put that in phasor form. Calculate your magnitude and your phase angle for that. Now I put the term times V2 in phasor form, now that I just have a single real, single imaginary number. Calculate the square root of 1.47 squared plus negative 1.11766 squared, and I get 0.95 phase angle of negative 1.11766 divided by 1.47 gets me negative 37.25. That whole thing times V2. How do I solve for V2? Simple. I just take this number divided by this one. So V2 gets me 206.85. That's taking 197.544 divided by 0.955. And for a phase angle, negative 51.54 degrees. That's taking negative 88.79 and subtracting negative 37.25. Gets me negative 51.54. That is my answer for the voltage 2. Again, I already knew V1, and from that, if I need to know anything else, I know everything about my circuit now. Once I know all those nodal voltages, that's the voltage drop across capacitor 2. It's the voltage drop across resistor 2. I needed to find the current through capacitor 2. I could just say V2 over ZC2. If I needed to find the current through resistor 1, I could say it's V1 minus V2 over R1 plus ZC1. Give me how to write all those terms originally when you were doing your nodal analysis setup. So once you've done that, you know everything you want to know about the circuit. I know this algebra is a pain in phasor form and it sucks. I promise I will try to make it that you're not doing so many of these problems on the final exam, or what you're doing could be a little faster or just setting up equations, but you do need to practice these until you're comfortable, particularly switching back and forth, phasor, rectangular form, rectangular phasor, adding, subtracting, multiplying from that. It's really the same circuit rules we learned before, besides that new superposition technique when we have different frequencies, but the algebra becomes a little more complicated. So good luck, guys.